Hi there, this is Professor Shannon Gracie. We are working out of the Precalculus Enhanced with Graphing Utilities text by Sullivan and Sullivan, and today we'll be covering properties of logarithms. Let's warm it on up. We've got a couple of problems here, and the first one is show that log base a at 1 equals 0. So go ahead and pause the movie and warm it up. All right, let's see how you did. If we take a look at this problem, log base a at 1 equal to 0, let's switch it into exponential form. This is true if and only if. So the base grows up tall. A logarithm is an exponent. So what's our power? Awesome, 0. And what's left is the equals 1. So what do we get? A to the 0 is 1. 1 does indeed equal 1. So you showed that that is true. Okay, let's see about the next one. Again, going from logarithmic form to exponential form. So the base grows up tall. A logarithm is an exponent. And then what's left? So a does indeed equal to a. And we have shown these two properties. So in summary, what have we found? We found that log base a at 1 is equal to 0 and log base a at a is equal to 1. So let's go on to some general properties of logarithms. I apologize ahead of time. I must have been tired when I was making the notes, and so there might be some changes. If you're working with a revised edition, I've probably made the changes already. But bear with me. We'll make some changes as we go along. So let's let m and a be positive real numbers with a not equal to 1. And let's let r be any real number. So first property here, if you evaluate an exponential expression base a at a logarithm of the same base, you get what's inside the log because you're evaluating a function at its inverse. Similarly, if you evaluate a logarithmic expression base a at an exponential of the same base, you just get what's in the power of the exponential out. And again, that is found from evaluating the function at its inverse. So let's take a look at this. So log base 6 at 6 is equal to, perfect, 1. How about log base 12 of 12 to the 4th? Do you see the bases match? So what do we get? Awesome, we get out what's in the power. And you could have really done this with the 6 to the 1. What about over here? Perfect, that's 0. The power to which I raised 9 to get 1 is 0. And this guy? Good, you have an exponential base 7 and a log base 7, so you get out what's inside the log. All right, moving along, the product rule. So if we now will have mn and a is not equal to 1. Let me make sure I wrote a not equal, I didn't even write it up here, a not equal to 1. All right, so m, n, and a are positive real numbers. A is not equal to 1. Okay, so the logarithm of a product turns out to be the sum of the logs. And we'll be proving this one down below so you can see why. So let's show why this is true. So proof. let's let x equal to log base a at m, and let's let y equal to log base a at n. So what happens when we switch those to exponential form? Good. We would get, working from this guide, you see we would get a, because a is the base, x is the power, and m is what's inside the log. And so over here we'll get a to the y is equal to n. Now, let's take a look at log base a of m times n. This is going to be equivalent to substituting in a to the x for m and a to the y for n. We'll have log base a of a to the x times a to the y. So this is what we substituted in. Alrighty. So what is this equivalent to? Good. We have the same base, so we can add the exponents. Now, using that property, do you see we're evaluating logarithm base a at exponential base a? So we're just going to get x plus y. But back substituting, what do we have? X was good, log base a m, and y was log base a n. So you proved it. Awesome. Okay, so let's expand each of these logarithmic expressions. If you want to pause the movie, go ahead and do so, and then we will, you can check and see how you did. All right, let's see how you did. This will be equivalent to, we have a product in this log, so we'll have log base 6 at 6 plus log base 6 at x. Now, what can we do? What is log, the power to which we raise 6 to get 6? Great, that's 1. And then we still have log base 6 at x here. Okay, so here, this is sort of, I'm going to show you where this power rule is going to be coming from soon. Do you see x times x is x squared? But if we look at it like this, this will be natural log at x plus, great, natural log at x, which is how many natural log of x's? Awesome, 2. All right, so now on to the quotient rule. Let's let m and a be positive real numbers, and a is not equal to 1. So log base a of m divided by n is equivalent to log base a at m minus log base a at n. So the logarithm of a quotient is the difference of the logs. So let's go ahead. If you want to try proving this one yourself, go for it. We'll show you why this is true. So starting off the same, right? Let x equal to log base a at m, and let y equal to, perfect, log base a at n. So if we switch these into exponential form, we'll have a to the x is equal to m, and a to the y is equal to n. So log base A at m divided by n will be equal to log base A at a to the x divided by a to the y. So again, a to the x is substituted in for m, and a to the y is substituted in for n. So this will give us log base A of, great, a raised to the x minus y. And we'll have x minus y, because we're evaluating a logarithmic expression base A at an exponential base A, so we get what's in the power. And this was back substituting log base A at m minus log base A at n. So you're done. Okay, so let's practice. Expanding, we'll have log 1. So what base does that log have? Good, it's the common logarithm, so it's base 10. So that'll be log 1 minus log x. But what is log 1? Good, 0. So at the end of the day, we'll get negative log at x. And over here, we'll have log base 4 at x minus log base 4 at 2. Can we do anything with that log base 4 at 2? Isn't the square root of 4 equal to 2? So the power to which we raise 4 to get 2, I believe, is good, 1/2. So typically what we'll do here, notation-wise, we'll bring that negative 1/2 to the front so that you know it's not in the log. If I had meant to write log at x minus 1/2, I would have had parentheses around the x minus 1/2. Okay, so next up, the power rule. So let mn, actually, we don't need n for this one. So this is where we get some edits. Let m and a be positive real numbers with a not equal to 1, and let r be any real number. So what we'll have is log base a at m raised to the r is equal to r times log base a at m. So the logarithm of a power is the product of the power and the log. And this is really powerful and helpful for solving logarithmic equations. So let's expand. You remember what we did in that earlier example, natural log at x times x, and we got 2 of those natural log of x's. Well, now we have the common log, so using that power rule, the 2 is a multiplier, and we'll get 2 times log at x. And we're done. Now with this guy, if you have a radical, you may want to write the radical using rational exponents. So now using the power rule, we'll have 1/2 times log base 5 at x. And we're done. Okay, so properties for expanding logarithmic expressions. So basically, this is just sort of a summary of this stuff. We want positive m, positive n, and then I want to keep the notation the same. Let's change this to these bases to a. I don't want to switch up the base, and we're going to change the r the P to an R, okay? The P is an R. And then, of course, we have A greater than 0 and A not equal to 1. And we have R belongs to the real numbers, is an element of the real numbers. So this is kind of going the other direction. If you see a sum of logs and they have the same base, you can condense it, right? So this will be log base A at m times n. So to expand, right, if you would write it as a sum of logs. To condense, you would write it as that product. Okay, so what's this guy going to be? Log base A at? Perfect. M over n. If you want to do parentheses, you can. You don't need to. And then this one will be? Awesome. Log base A at m raised to the r. So just a summary of the properties we just learned. So let's expand these. These are a little more mean. So what should we do? We'll have, perfect. I'm thinking we should rewrite this as log at x to the 4th times y minus 1 to the 1/3. So then we have a product, right? So we'll have log at x to the 4th plus log at y minus 1 to the 1/3. Using the power rule, we have 4 times log at x plus 1/3 times log at y minus 1, and you're done. A lot of times people want to do, make up a little of their own math with that log at y minus 1. But if you look at the properties, you'll see that there would be no property where you could bring the log to both the y and the minus 1. Okay, how'd you do? Awesome. Let's look at this guy. So let's just do this first of all. We have log base 2, and we have this whole quantity that's being raised to the 1/2. So I'm going to move over to the left a bit. This will be 1/2 times log at x squared plus 5 divided by 12y to the 6. And then this will be 1/2 times log at x squared plus 5, and that's log base 2. I apologize there. I need to write my base. And then minus log base 2 at 12y to the 6. So then we'll get 1/2 times, we're done with the first expression, but the second one we can write as log base 2 at 12 plus log base 2 at y to the 6. And then finally we'll have 1/2 times log base 2 at x squared plus 5 minus log base 2 at 12. There's technically a little more we could do with log base 2 at 12, but we're good for this at this point for that. And then we'll have minus 6 times log base 2 at y. And then we'll be all done. All right. Now, properties for condensing. This is when you're going to go the other way. And I'm going to make the same, changes that I had made so that these look similar to the properties we had done. So if we have for m greater than 0 and n greater than 0, a greater than 0, a not equal to 1, and r is a real number. So if you have a sum of logs, you can condense it. And this is useful for solving logarithmic equations. By the way, what we were doing before is really useful in calculus. When you're doing derivatives, it's much easier to evaluate the derivative of an expanded expression than it is a condensed expression. Okay, so here this will be log base A at m, good, minus log base A at n, and this one will be perfect, r times log base A at m. Okay, so let's write these as a single logarithm. So you kind of go backwards. If there's any powers, you bring them in. So this one has, we can rewrite the first term as natural log at x cubed, and then minus natural log at x minus 2 to the 1/4. Now we have two logs that have the same base of e, and we're subtracting them. So we can write them as one happy log, and they're going to be divided perfect. And then if you want to, you could rewrite this so that you've got it in radical form. Sorry, that base is kind of big. So the fourth root of x minus 2. All right. Let's do this next guy. Again, please pause the movie and give it a try yourself, and then check and see how you did. All right, let's see how we did. This will be equal to, can't do anything with the first term yet, so let's bring that 12 in as a power. So it's going to go in as a power. Now we have two terms, both of them have a logarithm with base 4, and they're being added. So we can write this as the product. So wait a minute, put base 4, and it'll be the product of 5 times x plus y raised to the 12th. And you're done. All right, next up, so this one again, there's some weirdness here. We're going to go ahead and scribble this out. Again, if you have the updated edition, don't worry about it. If you have the first edition, you're lucky enough to help discover the changes with me. So this proof is, or these two statements are coming from the fact that since y equal to log base a at x is a one-to-one function, and if, of course, m is greater than 0, n is greater than 0, a is greater than 0, a is not equal to 1. And this is how you're going to solve, this way you can solve some log equations. So basically, if m is equal to n, then if you can get a log equation where you have the same base log on either side, right? So this first property we don't use as much in pre-calc, but you're allowed to evaluate the log of, well, actually we use it a bunch. I take that back. If you have an unknown power, it, like a variable in the power, then what happens is you're going to log both sides of the equation so that you can bring that down as a base. So this is when you would log both sides, and we usually will natural log both sides if for any base other than 10. If you have a base of 10, you would use the common log of both sides. So that's what that property is for. The second property here, going the other direction, is when you have a log equation and it was expanded, you do the work to condense it, then what you can do so if you have the same base log on either side and it's completely condensed, then what's inside the logs must equal each other. Okay? All right, so the change of base property is another powerful rule. So A is not equal to 1, B is not equal to 1, and M, they're all positive real numbers. Then log base A at M is equal to log base B at M divided by log base B at A. Why would we use this property? Do you remember earlier when I said, oh, we can't quite check these answers yet because we don't know how to graph logs with bases other than 10 or E? So here, this is going to allow us to be able to use our graphing calculator to graph these. And also to evaluate them on the calculator because we only have the natural log key and the common log key. So here we go. Use common logarithms to evaluate log base 5 at 23. So log base 5 at 23 is equal to log 23 over log 5, and that's approximately, let's get our calculator out. Okay, so the log key is here. So log 23, and make sure you put the parentheses at the end before you do the divided by. And then log 5, and enter. We get approximately 1.948. All right, now let's use our natural logs. So log base 5 at 23 equals natural log at 23 divided by natural log at 5, which is approximately what do you know? 1.948. What did you find out? They're the same. You get the same answer. Okay, so now real quick, we might as well, let's graph this one. So if we go to our graphing calculator and we go to y equals clear, clear. So the way we would graph log base 5 at 23 would be, I'll just use the natural log. Actually, this one, I'm sorry, this one's just going to be a constant. Let's do this. Let's do, because I think let's do this. Let's graph log base 5 at x instead. And then we could plug 23 in to see, to check an answer. So this would be log x divided by log 5. So natural log x divided by natural log 5. And look, that's our graph. Isn't that cool? And then you could go to second, calculate value, and put in 23. Whoops, I need to expand my window. I think I'll just do y max of, well, yeah, I think we'll be good. All right, so now we'll go to second, calculate value. Oops. I think I put something weird. Okay. Graph. Third time's a charm, right? Second, calculate value 23, enter. And look, that's what we got. Finally. All right, here we go. Okay, so now you know how to graph a log function that has a base other than 10 or e. All right, so we might as well. There we go. So let's go to our application. So the application is using this difference quotient, which you'll see a lot in calculus, and we want to show that the difference quotient for f at x equal to log at x is this expression here. So let's do it. F at x plus h minus f at x divided by h equals log base a, so we'll replace x with x plus h, and then the other part is just log base a at x all over h. So f at x plus h, actually I'll do it down here, f at x plus h was this. And of course, f at x, sometimes it's kind of like so easy it's hard, right? F of x is what was given up here, right? Okay. So this is going to give us, we have a difference of 2 logs with base a. So this is equivalent to log base a at x plus h divided by x divided by h. Well, if we make a couple of adjustments here, if we divide through by x, do you see we'll get 1 plus h over x, that's within the log. And then we could times this by 1 over h. When you're dividing by h, it's the same as timesing by 1 over h. And then let's just switch the scalar to the front, the constant to the front, and we have this. And finally, using the power rule to condense, we'll have this guy will go in as the power, and we'll have 1 plus h over x raised to the 1 over h. And you're done. You did it. Awesome. All right. So that, I believe, wraps it up for this lesson. So you have a fabulous day. Bye.